what the topic is about is, like many others, it's as deep as you want to go. And one of the things that I've learned with this hobby, or a number of things, is that the people who really get into it and get drawn into it, where they're willing to go out in cold weather like we have here, or to go to public star parties and bring their equipment like this down there to share with people, really want to do that. I mean, it's not an imposition, it's something they want to do. And something that I didn't learn about myself until I moved here was how important that was back in all the years I was in Austin, Texas, being involved in a large astronomy club. We had all kinds of projects going on. And we come up here and say, okay, there's hardly anybody else around that's showing any interest. And to just go out there and be in the dark by yourself, it gets kind of lonely. But especially when you see a pair of red eyes looking at you. And the most exciting time I've had up here with the telescope was I had it out in the driveway. Neighbors started yelling, and I heard a shotgun go off, and there was go bear and stuff like that, so I realized they had a bear. And I thought, I'm not going to give in to that. I'm going to stick it out here. And so I was over at my telescope looking through the eyepiece, and I heard this, and my adrenaline just went like that. And then in a second, I realized it was my stomach. But it got me. I mean, I thought, I can't do this. So I packed up and put stuff away, because we know there's one right in the area. But deer roam around and all kinds of other animals, so it's nice to have someone else out there to kind of give a little reassurance that it's okay. I'll give you a little overview. I'm going to start with the history of the telescope, and then some of the considerations that go into deciding what would be a good instrument for me to consider. And then after the break and the raffle, I'll go into the pros and cons of the three basic types of telescopes that are commercially available, which is basically, we've got the three represented here today. And there are literally hundreds of choices. And some people will ask, well, where can I find out more? Telescopes.com. About as simple as it gets. Majors retailer, they're not a manufacturer, but they're a retailer. And their print catalog goes on for about 30 pages of telescopes, and each page has multiple scopes with multiple sizes and arrangements. So just as one company probably has 100 choices. So I can be amazed, other than price, where do I go on? So that's what I try to address today. And this has already covered a little bit about my background, so I need my iPad to stay on topic here, and make sure I don't overlook anything. So before we get too far into this, let's not make an assumption that we all know what a telescope is. Okay, in general, a telescope is to enhance what you can see with your eyes. And there's even an argument for your for your eye to be a one-power telescope. So what can a telescope do to enhance your view that you have with your normal eye? Magnification? Yes, that's critical. Because our view, which is just one power, that's what we compare it to, is our normal view, is just one power. And so anything that has finer detail than what our retina is capable of resolving, is a technical phrase. In other words, our rods and cones are bigger than the image we're trying to find detail, but you can't see it. And this includes things like just looking at the moon, saying you can actually see craters. No one can. A few people claim they can, but you can't confidently say, I'm seeing craters. You can see big blotches or lava flows and some other colors, but you can't say you see craters. And so magnification is a critical feature. Okay, one other thing, especially for astronomical telescopes, other kind of things that we need help over our regular eye. Most things you're going to be looking at other than the sun, moon, and planets are dim. So we need more light. And our pupils are restricted to about 1/4 of an inch, about the size of a number 2 pencil. And that's all the light you can get in there unless you have some help. So light gathering capability and magnification are 2 critical features. Now, one reason I bring that up is that just because they're fundamental doesn't mean they go away when you start looking through a catalog and making decisions. That will come back into play. Especially like light collection. I could be looking at things where I need lots of light versus looking at the moon where you got more light than you can deal with. Those fundamentals will still come back into play. So get into the history a bit here. In the early 1300s, the first eyeglasses started appearing in portraits and in some of the literature being mentioned. So the idea of how to grind lenses and make duplicates, because most people's eyes, both eyes are usually have the same problem. And so to make duplicate lenses and then some way of hanging them out in front of you. This technology is, 800 years old? So it really hasn't been improved on much rather than the accuracy of the lenses and the different kinds of frames to pick from. So we're going to make a leap here from 1300 to the first decade of the 1600s. It's 300 years. So something I'll kind of reference to because as we go along, things start happening faster and faster. But when you're talking about that far back, it took 300 years for someone to take a lens, hold it up in front of them, and put another lens here and go, wow, it's bigger. It magnifies. Well, I'm sure they didn't have that word back then, but just arranging 2 lenses in line like that and discovering that it magnifies was a big deal. We know who did that. There's a head shake over there. Yeah, you're right. Is that not Galileo? Excuse me?
Who was it?
Who was it? I'll give you the answer. We don't know. Good question. But we do know 3 individuals by name, Europeans, that within about a year of each other, in the very early 1600s, filed patents in their respective countries. But each patent office said just hold 2, put 2 lenses maybe in a little paper tube that shellac. Even making a tube in the 1600s, how would you make a tube? You didn't have plastic, fiberglass, sheet metal, plastics, something like that. You have to have another technology in order to have a tube because they didn't have to use for them. So no individual person has been given credit for the discoverer of it. Now what Galileo has been actually attached to was that he learned about telescopes from someone who described them to him. He didn't actually even have one because they were basically sold at fairs and carnivals as a toy or a novelty, and they only had about 3 power. So they were just easy to make and they'd be sold for a profit, and that was kind of the extent of it. But when he learned about it and it was described in detail, being a scientist, he wanted to know how to do that. And he did it by experimentation because he had nothing to go on. No one else had ever done anything. And he gradually figured out that if you take, this thing is a little shaky, so hopefully we'll not have an accident here, on edge, if you take what's called a convex lens, so where both sides are bowed outward, and grind that, where it's nice and polished, that when light rays come in and strike the surface, something happens. When you change, it's called a medium. When you go from one medium to another that has completely different density, you're going from air to glass, is a huge change in density. it will actually bend. And when we exit out the other side, it bends again. And this is called refracting, the technical phrase for it. So telescopes use this. And we'll go ahead and show you this one, which has a lens in the front. This is the classic design, is a refracting telescope. And then the other thing that has to come into play here is, in the simplest of ways, you also need a lens here to affect like a magnifying glass. It examines the image that is formed by the first one. And we, of course, now today refer to that as an eyepiece, but in the very first one it was just a single lens. But this is where the idea of just holding two lenses up, you can make this happen. We'll have any control over it. This needs to be put into something stable like a tube and be adjustable. We've all seen, the pirate films and stuff like that where the guys are racking out those things and just putting them back together. Well, they could adjust for distance and that kind of thing to focus. And that's basically all they were doing. But some of the problems they had back then was that the glass was mainly manufactured for things like drinking vessels and cooking vessels, and there wasn't any concern for looking through the glass. And so when they started trying to grind lenses, the people who actually provided glass, which is just melted sand, they had a lot of impurities, bubbles in it, and so even Galileo, when he made his first one, was pretty imperfect. I mean, it may have been drowned fairly well, but the glass was bad. And he had to take and put in front a paper washer, and they actually have this telescope in a museum, and I've seen photographs of it. It's actually a piece of paper with a little hole in the middle, a little bit bigger than your pupil. So his first telescope that he manufactured didn't gather much more light, and everything he discovered was bright as a result. But what he did in his analysis was taking that little 3-power toy, and he made one that focused much further back and could amplify more. He made a 30-power telescope, the very first one. And with that, he discovered 4 basic things. Sunspots, which got him in big trouble because it was widely regarded that the universe was perfect. And those little spots that slowly moved across, appeared to move across, actually the sun rotated. But that kind of created an issue there that we shouldn't know about. And then the moon. He found craters and mountains, which had never been seen before. And he sketched them. And he watched as the lunar day goes along, the shadows that they cast, even craters, the wall being rough, cast shadows. You can watch those shadows move, which is still a lot of fun to watch. You can see that progression. But he recorded this, and that would confirm that it's orbiting, it's moving in relation to the sun. All these kind of things that are obvious to us today weren't obvious back then. And the next thing, the third thing he discovered was Jupiter had moons. And when you look at Jupiter, it's slightly oval because it spins so fast. And sometimes you'll look and you'll see the closest moon here, the farthest out there, and then one over here, and then maybe one here, and then an hour later you look and this guy here has moved and maybe is on top of the planet, which is really fun to watch, especially if it's casting its own shadow. And there's still things that are very interesting to do. But he recorded this. He applied science, which means you make observations, you record, you make conclusions, you make predictions. Okay, I've seen this particular one come around, hit the same spot in X amount of time. Repeat it, okay? I estimate that at a particular time it's going to be right back there in that same spot. Okay, it is. That proves that my observations are accurate. That's science. That's what Galileo did. He was the first one to use the telescope to do scientific observations. Other people have just played with them, in essence. And then the fourth thing that he discovered was Saturn. And the way, well, I'll just go ahead and use Jupiter because they're both just sort of slightly oval planets. And what he saw when he looked at Saturn was that his optics were bad, and he couldn't make out anything. I mean, the people who look through that telescope today say that it is awful. That he discovered all this with that instrument is truly amazing. But he saw it like this, and his conclusion was it was a triple planet. And it took about another 50 years for the technology to advance to the point where they said, no, it's actually a ring system, something like that. And hence the person who discovered that had his name on the probe that was orbiting Saturn for about the last 10 years, until about 10 years, about a year ago when they had to destroy it. Cassini was his name. But that's what Galileo was able to do. Now let's jump ahead 150 years, mid-1700s. Sir Isaac Newton came up with the idea, him and several others, but he's the one giving credit for it, that if we were to take a tube, and they do have his original telescope, but it's made out of wood, so they could, by then, cut thin slats. I don't know whether they glued them or how they bonded them together, but they figured out a way to make a tube out of like a canoe, in fact. And his idea was that at the bottom of this tube will have a mirror, and it will have a concave surface, or it dips inward. And what we'll do is let the light come in, come all the way down the tube, and when it strikes, it will come back and reach a focus here. Well, that isn't very practical, because you have to keep, to not cause a bunch of wild distortions, you have to have the mirror sending that light straight back the way it came in, and so in order to put an eyepiece here, where's your head going to be? Right in front of the tube. Which, in a small telescope, would block everything. On a bigger telescope, you'd have all your body heat rising right in front of it, which on many of these scopes, if you have to go to one of our star parties, you just reach around and put your hand there, and you just see the waves coming off of it. The telescopes are very sensitive to things like that. So Newton came up with this idea. Let's put a small mirror out here. This is the primary, so this is the secondary, and send the light at right angle to the side of the tube. And we can have our eyepiece here with some way of focusing it. And we'll come up with what has been, in his honor, a Newtonian. I'm going to move over here and we'll look at one of these. And I'm going to give Wilson the first shot at it here.
Just a second. Let me get in. Okay.
And I'll sweep this across, and as you look down the tube, also notice out in front here by these little metal veins, 4 of them coming across, that's the back of the secondary. It's usually a plastic holder, but the mirror's on the other side where you really can't see the reflective surface of it. And then the eyepiece holder is here, and it has the method of moving the eyepiece up and down to get focus. And these metal veins here holding the secondary mirror are called the spider. It kind of looks like that. But they also create an interesting effect that all of you have seen many times. When light passes past an object, it's like putting a rock into flowing water. It kind of has to go around it, and light does the same thing. It's just normally it's so microscopic with our regular eyes, we never see that happen. But we all see them in photographs. The bright stars all have the 4 spikes coming out of them. 1, 2, 3, 4. That's what's happening. Even on the Hubble photographs, when you look at those, The brighter stars have 4 spikes on them because it has a secondary holder, a spider, like that out in front of it. And it's caused by a disruption of light, which is not good. Because if you're doing that to that light, putting it out in those spikes, it's not in the image where you want it, so that star is losing. Even the ones too faint to see that they have spikes are losing light to spikes that are faint, making those stars fainter than they should be. So that's a trade-off in this design. We give up some of the light because we're interfering with it coming down the tube, even with something as thin as those metal vanes. Now, what did Newton have? He didn't have sheet metal. Actually, he had one big thing sticking down there holding the mirror rather than 4 of them. Yeah, just something made out of wood, probably a wooden dowel. I don't think they have his original telescope still. All those things, they get lost through time.
So is magnification gained by doing that?
Not necessarily gained, it just depends on this distance. With any given eyepiece, it's this focusing distance that determines how powerful this eyepiece will perform. And it's very simple mathematics of the focusing distance of the eyepiece divided into the focusing distance of the main instrument. Just simple division. So if you have a much longer focusing thing, this is going to divide into it many more times, which means that much more power.
So what prompted him to do that? What's the advantage of having a mirror versus the other metal?
Thank you for doing that. I mean that sincerely. Okay, this up here looks real simple. If you block off that top part, you just saw that little element of the glass, and it looked like the edge of a prism, like you've seen in your high school physics class. A prism has flat sides. Okay, this guy's got a little bit of a curve to it, but basically it's the same thing. So when light comes through, refracts, the red goes out the farthest. Green comes to focus a little bit shy of that, and the blue comes to focus even closer than that. That creates the color spectrum, the rainbow. And so in effect, what we have here is that all the light that was combined, making white light as it goes through the prism, gets spread out. Well, that creates the color spectrum, which is helpful for some things, but for a lens, you come out here and you've got the red and the green and the blue, while we're drawing all the lines, coming to a different point of focus. So when you have the eyepiece here and you're trying to focus it, where are you going to stop? So in effect, it's like looking down a tunnel of color. And so the light from whatever object you're looking at, rather than being all concentrated in one nice little flat image that we put the eyepiece on, instead it's spread out. Now we're talking about maybe a 16th of an inch or less. But still, that light is spread out, so as you try to focus, you're only getting a particular color at any one time, and the rest of it is just thrown out into the background as a bright rainbow of color. Well, that limited a lot of discovery work with these early telescopes because of this. And so that issue, it's a color distribution issue. Light reflecting off a mirror doesn't do that. All the colors stay together. So this was the draw to go to mirrors and to solve this issue here, but they had another issue that would take them another 150 years to solve. Yeah, this mirror, they had not developed the technology to put a silver surface on glass to make a mirror. That had to wait until almost 1900. What they did do was they took a metal that they could polish real smoothly and get a bright finish on it, and that was a form of brass. Okay, so you spend a couple of 100 hours on a bigger mirror. You will spend a couple of 100 hours getting it to that final perfect shape. Some people do that even today. They like grinding their own optics. So what happens to bare brass in a moist climate like England, France, and Italy in 4 to 6 months? You get corrosion, tarnishing, but it's worse than that. It's actual pitting of the metal. It's the destruction of the metal surface. And you want that metal surface to a level of perfection in flatness beyond anything that we know in normal life. And that's why some people enjoy doing this, because you're working to perfection. And when you do it right, it comes out and you look through that eyepiece, and I did that all the way through. So I always buy mine because I don't want that much grief. So every 4 to 6 months, they would have to take the mirror out and completely rework it. Another couple of 100 hours. And so there was quite a penalty. And they even worked up to, I think the largest one in that early period was a 4-foot diameter mirror. That's thousands of hours. And so it just got to be impractical, so reflectors kind of moved to the background. It just couldn't keep up with this much work on it. Now we'll go back in the almost same time period, and let's look at this issue. And someone, in fact, there were several opticians at one time said, let's add another lens. Typically, they mirror that back curve and come out, and the back edge sometimes is flat, sometimes it has its own curve, but they use a glass of a different density. There's a different source for the glass, so that you have a very subtle change of medium, but we can get the red and the green to come together, and we're only left with the blue sticking out there by itself. And this is called an achromat. And the reason I put that up there is even today, around Christmas time, you walk into Walmart or Sam's or something like that, and we have a case of those, a skid of those, and somewhere on there, this being what is a refractor? I forgot to look at, I assumed it was a reflector. Because a lot of times they'll have in big type there, an achromat, like, oh, some big fancy word. Well, it's been around since the mid-1700s. But they were able to get 2 colors to come to focus, which was a dramatic improvement. But bright objects like a first magnitude star and the moon have blue halos around them. Now, one of the things I'll point out later is in recent decades, they've come up with adding a third glass. They call it exotic glass, meaning doesn't form in nature. And they can't hardly make them bigger than 6 inches. They just cannot get them to come out in a form that's workable. They'll break or have bubbles in them or something, so 6 inches is the limit. But with that third, they can get all the colors to focus if you got the money. We're talking about $500 to $1,000 an inch in diameter. So if you want to spend $4,000 for a telescope of this size, which only includes the 2, no eyepieces and none of the mechanical parts. Oh, they're beautiful and they're fantastic performers. People especially like perfection. And some people, you burn the money and you want that, and just like having a watch or something that was nearly perfect. Some people just want to have that, and there's a market for it. Yes.
And how much further could Newton see than Galileo with that particular design, do you know?
Well, distance isn't really a factor, because if you have something bright, that's what you're asking.
Yeah.
If you have something bright, it could be at the edge of infinity, and if it's bright enough, you can still see it with your own eye. So distance really isn't, it just depends on what it is you're looking at. And that's a common question. But the real truth goes back to the fundamentals. How dim of an object can you see? Because if something is a real elusive nebula, it may not be particularly far away, but it may be extremely hard to detect because it's so faint. And that may be what someone wants to know more about. So distance really isn't manufacturing, the reputation, and these will be steady too. I don't think you could make that yourself. You'd have to have a lot of equipment. This you can do with a hand tool. You know, what is it you want to do? Well, you want to just pick it out of the catalog and be ready to roll in a couple of days, or you want to spend a couple of months, you know, making it? Most people have gone this route today. There's not too many people making the drone anymore. Because they got so cheap, disappeared, and they're so good. You had to go, but I'm trying to run through some of the advantages. You've probably kind of gotten the gist of a lot of that from what I've already said, but in general, refractors have the advantage of their sealed tube, which keeps the dust out. And like I said, you know, cleaning optics is a chore. It's got to be done right, or you just mess them up. They're usually ready to go. And what I mean by that is minimal cool down time up here. So if you take a telescope out from a heated house outside to sub-freezing temperatures and the temperatures are dropping, a refractor can handle that better than the other two designs. Kind of mix in, reflectors are awful. Mirror in this 10-inch telescope is probably 1.5 inches thick of Pyrex. And if you go out with 20, 30, 40, 50 degree difference between the mirror and the air, that mirror is going to be flexing and warping. You know, you'll just be trying to focus on fuzz and you'll just be dancing like that. So with a scope like this, and mine is a little bit bigger, is as soon as the sun gets low, I bring it out. And it may be another 2 hours before it's really dark because the sunlight lasts so long, twilight does. You got to plan ahead. You can't say, wow, it looks great tonight, and go grab it and pull it out. A refractor is your best choice if you want that. But reflectors or even the SCTs, you got to plan. The refractors, because they're the really good ones, are built, like I said, near perfection, are ideal for things like looking at craters of the moon, because some of the craters are incredibly small, and the detail even on the big ones, if you really want to see it in three-dimensional, you know, almost lifelike, then the refractor is the best. It doesn't have a mirror hanging out in front disrupting the light. That's the key thing. So they're great for that. And because they don't have a mirror out in front, they give the best contrast. And I was just reading a review last week where a long-time reviewer said, I have to take back that a little refractor won't do well on galaxies and nebula. He said, this one, the contrast is so excellent. In other words, it's not scattering light because of imperfections in the optics, that kind of thing. The difference between what little light is there and the black background is so good that it challenges reflectors much larger. So I found that pretty impressive, but so was the price. And the one thing that might come into play for you is the refractor is the only one of the three that is worthwhile using on terrestrial objects. In other words, like bird watching or something like that. To take an instrument out like this, like mine, the lowest power is 50. Well, if a bird was 50 feet away, it's going to look like it's 1 foot away. Well, I could barely fit the head, even the birds don't stand still. And so, and plus on refractors, there's a relatively cheap little device, a prism like you see in binoculars and give them the dog leg. You can buy one of those to put in the back of it and flip the image over. Because most astronomical telescopes, the image is upside down, reversed left to right, or both. And none of those are good for looking at things on the ground. And a reflector like this, most of them are set up with the eyepiece at 45 degrees. So when you look at something on the ground, it's either going to be this way or this way, and upside down. So reflectors are not good at all for looking at things on the ground. Okay, the refractor disadvantages, they're expensive. For their size, they're heavy and bulky compared to other designs, but you know, who's going to have a little 4-inch reflector? That's a toy. I mean, you're going to go 8 inches probably, because it's only a couple $100. I mean, but still, for their size, they're kind of heavy. Now, reflectors, lowest cost per inch. So if you're wanting to look at dim objects, the reflector is the cheapest way to get there. You get the most mirror, you get the most light for the cost. And you stand a chance, you know, you can maybe buy the bars and put it together yourself if you want. They're excellent for the faint objects. They're okay for the bright, close objects like planets and the moon. But understand that a mirror this big on the moon, if you look at that for more than a second, I mean, you sit there for maybe 30 seconds, a minute, and you step away, you can hardly walk because this eye is just going wow, wow, like that, and black flashes and stuff like that. And your other eye is seeing all kinds of faint stuff, and it really is hard to walk. I mean, it's like putting a stick in your eye unless you put a filter up here and knock the light down. What I do is I put a mask over it with a little hole over here, so it's like a refractor. It's not in front of the mirror, and so I don't have color problems because it's a mirror, and it's really pretty cool. I mean, just a big little piece of wood to do that with. Sometimes real simple solutions to the problem. Of course, we're paying for a big instrument, make it little, but okay. And reflectors have few optical problems. Until you get really deep like that, they don't have the color and other optical distortion issues. Pretty error-free, and that's why they're cheap to make. Disadvantages is quite often they call for alignment. See this guy? Yep, we've got adjusters, I can feel them. They're usually in 3 locations so that you can tilt the mirror around, and the secondary, oh, sorry, just knocked it out of alignment. That was just for show. And the secondary has 3 little screws here also to tip it around, but it's very, very sensitive to do that. There are laser devices that you can buy to put in place of the eyepiece that bounce a laser beam around, and one person can sit there and make the adjustments and watch the readout. And it's called collimation. It can be done in a couple of minutes, but again, it's a chore. Where a refractor, that rarely will happen unless you drop it or pour a liquid on it or something, and then you're going to send it back to the factory. The adjustment of the main lenses and stuff is not something for you just do trial and error. It really requires sophisticated instruments. Now, the Schmidt cast, I think it's the best all-around compromise of the different designs, the plus and minuses. It does well for deep sky observing. You can go up to 14 inch and still be portable. You've got enough strong people to help you. You can do that. And the other thing that's really good about it with that front lens is you keep an eyepiece in it. It's closed. Dust is rarely a problem. Treated with respect, and they'll probably stay in alignment for a long time. But if it does get out of alignment, they are very sensitive to adjust. They do make a laser device, but it's about $400, and that's all it does. Not useful for anything else. But if you have issues with it keeps drifting out of alignment, you know, that's something that has to be considered. Because if you're sitting there tweaking little screws and having to move around and everything like that, that doesn't take long before you decide, I'm just going to watch TV tonight. Really, that's the kind of stuff that happens, and it will happen more regularly and pretty soon, you know, it's not used. The disadvantage of the SCTs is they're somewhat more expensive than Newtonian, especially a basic manual Newtonian with no electronics on it. And the one other thing I'll mention here, the size of this mirror versus the one in here, even though this is an 8-inch, its secondary mirror is probably bigger in diameter than this one for a 10-inch, because it's having to intercept that steep cone sooner, and so it's got to be bigger. So you've got this big black thing that's blocking some of the light getting to the mirror. I mean, it just cuts down percentage of the amount of light that your mirror should be able to collect. If it was a refractor, that would be that much more light of a gain, but you can't buy a refractor this big. I don't know of any company that makes a refractor this size. There's a couple of 6-inch models on the market, and then you drop down to a few more 5-inch, and then a lot of 4 inches and smaller. But the cost of manufacture of these exotic glasses and grinding them and making them nearly perfect, when you start talking about something that big, no one can afford them. There's just not enough market. So if you really want a larger scope for going deep, you're looking at a mirrored choice. And the thing I kind of want to end on is eyepieces and some of the other accessories. This eyepiece like this is probably what most people kind of would visualize. And if we're looking at planets and the moon, this has what's called a narrow field of view. I would liken it, if you made a circle like this, put it about 2 inches in front of your eye, it would be about what it would be like looking through this eyepiece. This guy, let's see a comparison, similar difference in price. This has 8 optical elements in it. You know, in the refractor, we're talking about 3. This has got 8 in it. And that's not as many as some of them have. And this weighs about 2.5 pounds. I mean, this is significant. This weighs a couple of ounces. This probably has 4 lenses in it, much smaller, and probably most of them pairs that are identical as far as manufacturing. But this guy is called the spacewalk. It's like putting that rather than out here. It gives you a view so big that when I look in, I have to move my head around like this to see all the way out to the edge. And they make it's an 82-degree field. This was from the mid-1995. They have ones now that are 110 degrees. So it's like literally like putting your head through a porthole and doing this. I mean, you're just absorbed into the image, especially like the Milky Way and stuff like that. It just brings you right into it. And some people see 3-dimensional. It's an illusion, but the 3-dimensional view of it. But one like this that I paid, I think, $325 for 20-some-odd years ago, is probably closer to $500 now. But the man that designed these created the simulations for the moonwalkers, you know, to be able to feel like what it was going to be like to be up there. And he retired and went into amateur astronomy, and what? You know, that's not what it looks like. You know, it's not like looking down a tunnel. And so he created his own company, and now they're on almost all the magazines. He's on the inside cover.
Is there something in between?
Oh yeah, oh for sure. Yeah, there's a lot in between. And there's also some more expensive. Of course. But once you try this, like other things, there's no going back. And with my personal scope, it was okay with the eyepieces I had, but it just wasn't, something I was particularly excited about. When these became available, to transform the instrument. I didn't do anything else, I just put it in and just transform it.
So that's the part I want to.
And do you have a favorite site that you go to read reviews of telescopes?
I would say probably the Sky and Telescope, and it's spelled out, SKYAND telescope.com, not the ampersand. And they have a lot of reviews. And the astronomy also has a very well-developed website.
Well, you
And they do a lot of reviews also. But with this type of thing, you say, well, that's one. I got 3 of these. Because once you get into it, you say, well, I need something with less power, I want something with more power, because of what you're looking at. And they haven't been disappointed to do that. Yes.
And you might mention that with the lens, the eyepiece that you have on the right has a lot better eye relief. And if you wear eyeglasses like I do, it makes a world of difference. I can't see through the little lenses.
Yeah, that's one of the things when if you get into looking at the detail of it, like in the catalog, they will have the EF, eye relief, and that's how far up above this lens does your eye have to be to get focused? So if you want to make sure if you're wearing glasses, there's room for the lens of the glass. But now this company, which is Telvue, Telvue, which is this man's company, makes a line of eyepieces that are threaded here, and you can buy dioptic correctors to thread on, like putting reading glasses on. And so you can correct for your vision. Of course, it's not going to work for the next person if you're at a Star Party, but, and they also can custom make it if you have astigmatism. Of course, you have to be at exactly the right angle, just like your eyeglass would be, but that's something you probably can make a little mark or something. But you can, the company, and they're not the only one who have gone to that point, so that trying to make the visual experience as comfortable and easy as possible. But again, they're not cheap.
So they make those eyepieces across multiple scopes, so obviously the size of the insert, I guess, going out.
They're standard.
Okay, they're standard.
Yeah, this is 2 inch,
Yeah,
and this is
okay.
1.25 inch. The little cheap Japanese are under an inch, but that's usually all they're available in, those sizes. But you notice that the lenses are bigger than, this 2 inch restriction. So that actually some of the light gets bent out this way and then brought back in. The refractor is the only one of the 3 that is worthwhile using on terrestrial objects. In other words, like bird watching or something like that. To take an instrument out like this, like mine, the lowest power is 50. Well, if a bird was 50 feet away, it's going to look like it's 1 foot away. Well, I could barely fit the head, even if birds don't stand still. And so, and plus on refractors, there's a relatively cheap little device, a prism like you see in binoculars and give them a dog leg. You can buy one of those and put it in the back of it and flip the image over. Because most astronomical telescopes, the image is upside down, reversed left to right, or both. And none of those are good for looking at things on the ground. And a reflector like this, most of them are set up with the eyepiece at 45 degrees. So you look at something on the ground, it's either going to be this way or this way, and upside down. So reflectors are not good at all for looking at things on the ground. Okay, the refractor disadvantages, they're expensive. For their size, they're heavy and bulky compared to other designs, but who's going to have a little 4-inch reflector? That's a toy. I mean, you can go 8 inches probably, because it's only a couple $100. I mean, but still, for their size, they're kind of heavy. Now, reflectors, lowest cost per inch. So if you're wanting to look at dim objects, the reflector is the cheapest way to get there. You can get the most mirror, you can get the most light for the cost. And you stand a chance, you can maybe buy the parts and put it together yourself if you want. They're excellent for the faint objects. They're okay for the bright, close objects like planets and the moon. But understand that a mirror this big on the moon, if you look at that for more than a second, I mean, you sit there for maybe 30 seconds, a minute, and you step away, you can hardly walk because this eye is just going wow, wow, like that, and black flashes and stuff like that. And your other eye is seeing all kinds of faint stuff, and it really is hard to walk. I mean, it's like putting a stick in your eye unless you put a filter up here and knock the light down. What I do is I put a mask over it with a little hole over here, so it's like a refractor. It's not in front of the mirror, and so I don't have color problems because it's a mirror, and it's really pretty cool. I mean, just a big little piece of wood to do that with. Sometimes real simple solutions to the problem. Of course, we're paying for a big instrument, make it little, but okay. And reflectors have few optical problems. Until you get really deep like that, they don't have the color and other optical distortion issues. Pretty error-free, and that's why they're cheap to make. Disadvantages is quite often they call for alignment. See this guy? Yep, we got adjusters, I can feel them. Usually in 3 locations, so that you can tilt the mirror around. And the secondary, oh, sorry, just knocked it out of line. That was just for show. And the secondary has 3 little screws here also to tip it around, but it's very, very sensitive to do that. There are laser devices that you can buy to put in place of the eyepiece that bounce a laser beam around, and one person can sit there and make the adjustments and watch the readout. And it's called collimation. It can be done in a couple of minutes, but again, it's a chore. Where a refractor, that rarely will happen unless you drop it or pour a liquid on it or something, and then you're going to send it back to the factory. The adjustment of the main lenses and stuff is not something for you just do trial and error. It really requires sophisticated instruments. Now, the Schmidt cast, I think it's the best all-around compromise of the different designs, the plus and minuses. It does well for deep sky observing. You can go up to 14 inch and still be portable. You've got enough strong people to help you. You can do that. And the other thing that's really good about it with that front lens is you keep an eyepiece in it. It's closed. Dust is rarely a problem. It's treated with respect, and it'll probably stay in alignment for a long time. But if it does get out of alignment, they are very sensitive to adjust. They do make a laser device, but it's about $400, and that's all it does. Not useful for anything else. But if you have issues where it keeps drifting out of alignment, that's something that has to be considered. Because if you're sitting there tweaking little screws and having to move around and like that doesn't take long before you decide, I'm just going to watch TV tonight. Really, that's the kind of stuff that happens, and it will happen more regularly and pretty soon, it's not used. The disadvantage of the SCTs is they're somewhat more expensive than Newtonian, especially at basic manual Newtonian with no electronics on it. And the one other thing I'll mention here, the size of this mirror versus the one in here, even though this is an 8-inch, its secondary mirror is probably bigger in diameter than this one for a 10-inch, because it's having to intercept that steep cone sooner, and so it's got to be bigger. So you've got this big black thing that's blocking some of the light getting to the mirror. I mean, it just cuts down percentage of the amount of light that your mirror should be able to collect. If it was a refractor, that would be that much more light it would gain, but you can't buy a refractor this big. I don't know of any company that makes a refractor this size. There's a couple of 6-inch models on the market, and then you drop down to a few more 5-inch, and then a lot of 4 inches and smaller. But the cost of manufacture of these exotic glasses and grinding them and making them nearly perfect, you start talking about something that big, no one can afford them. There's just not enough market. So if you really want a larger scope for going deep, you're looking at a mirror